So hi everyone, welcome to the Weekly Space Hangout for Friday, February 5th, 2016. I'm Fraser Cain, publisher of Universe Today, and this week we've got stories about the creation of the Moon, chimps in space, shaky plans for Mars, the age and density of Saturn's rings, more information on 67P, Earth-hiding stars, and a black hole jet. And we've got a special guest, but we'll get to that in 1 second. So, joining us this week, we've got Alessondra Springmann. Sandy.
Hi.
Carolyn Collins Petersen. Carolyn,
Hi.
welcome back.
Hi.
Jolene Creighton from Petersen. Hey, Jolene.
Hello, Fraser.
Morgan Rehnberg. Morgan.
Good to be here.
And we've got a special guest, Dr. Or Graur from New York University. All right, so let's start with the special guest. So, Dr. Graur, why don't you introduce yourself and let people know who you are and what you do?
Okay. Hi, everyone. Hi, Fraser. My name is Dr. Or Graur. As you said, I'm an assistant research scientist at New York University and a research associate at the American Museum of Natural History here in New York City. I am an observational astrophysicist, which means I either do observations at telescopes, which I personally don't do that much, but mostly analyze data from telescopes. And I am a postdoc, so I have a PhD, but I don't yet have a professorship.
Right. Now you specialize, what kinds of observational astronomy do you specialize in?
So I try to connect between supernovae, explosions of stars, and the types of stars that end up exploding as the different supernovae we observe. And my PhD was specifically on type 1a supernovae, the ones that were made famous because they're used to measure distances to faraway galaxies, and those measurements were used to show that the expansion of the universe was accelerating, which led to this idea that maybe there's something called dark energy that's causing this expansion.
Okay, so just to give people the background, right? Your regular garden variety supernova is when you have like a star with a lot of mass and it, the core collapses and then the thing detonates. But these type 1a supernovae, they're a different creature. So can you explain the process that happens to get one of these type 1a supernova to go off?
So as far as we understand, this is a thermonuclear explosion of a white dwarf, which is the dead core of an old star. Stars which are a few times more massive than our sun. They won't go through the process that you described. They won't have core collapse. They'll stop fusion in their cores after they reached carbon and oxygen. They'll blow off the hydrogen and helium envelopes, and so you'll get what we call planetary nebulae. And then the white dwarf, the dead core, will just sit there and cool down for eternity, basically, unless you do something to it. So we think that in order to blow up, you need this white dwarf to be in a binary. And so the question then becomes, what is the nature of the binary companion? And what exactly does it do to the white dwarf to cause the explosion? And that's what I try to figure out.
Well, don't leave us hanging.
So we don't know yet.
But it's a star, right? I mean, it's not a, it's some kind of stellar object, right?
Yes, we think so. I don't know of any scenario that calls for something else.
Right.
The most popular scenarios have their companion be either a main sequence or a slightly evolved star, maybe a red giant, and then the white dwarf seals hydrogen or maybe helium from the other star and accretes that hydrogen onto its surface. And when you do that, you raise the pressure and temperature in the core of the white dwarf until you get to a temperature where you can ignite carbon. And then you ignite it under degenerate pressure. That leads to a thermonuclear runaway and the whole thing that just blows up.
Right. Okay. So the star in this case is already so compressed and it's mostly carbon, they call them the biggest, most massive diamonds in the universe, right?
Mhm.
That it's already super compressed, that it's never going back to be a normal star. It's not like if you give it a bunch of hydrogen, it's just going to start the fusion process and continue on. Because it's so compressed, that causes the detonation of the carbon.
Because it's so compressed, yes, you can reach thermonuclear runaway. That's where that comes in. Now that's one scenario. The other leading scenario has two white dwarfs instead of one white dwarf and another type of star. This time you have two carbon-oxygen white dwarfs, and this time the two of them are in orbits around each other, and those orbits will decay due to loss of energy to gravitational waves until the two white dwarfs merge. And then once again you have the necessary conditions to ignite the carbon and blow up.
Wow. So, I'd like to talk a bit more about the actual stars themselves. I mean, I think the Holy Grail in this science is to spot the progenitor, right? To see one of these places before it goes off as a type 1a.
So for that to happen, we would need a type 1a supernova in our galaxy. These white dwarfs are just too faint for us to see the progenitors in faraway galaxies. So we do try to do these pre-explosion searches, but they only give us upper limits on the luminosity of the stellar system underneath. This works wonderfully well for other types of supernovae. For ones where the star that blows up is a red supergiant, for example, we actually do see the star in a pre-explosion image, and then you wait a while and you see how the star is no longer there. And that's the smoking gun. That would be wonderful.
Yeah.
But for type 1As, the white dwarfs are just too faint.
And so let's talk a bit about, the importance. Before this was just one interesting astronomical puzzle, but now these type 1As have truly been the key to understanding this bizarre concept of dark energy.
Right. So I study them just because I like to know. I like these puzzles and I want to know what blows up. But the cosmology crowd want to know what these are to rule them out as a systematic uncertainty in our derivation of the cosmological parameters. Because when we do cosmology, we assume that all the type 1a supernovae we see at high redshift, so way back in the universe's past, are essentially the same beasts as the one we observe near home. And that's a little problematic as long as we don't know exactly what type of star blows up, whether that type of star changes as a function of redshift, maybe it has some dependence on the metallicity of its environment. Even worse, maybe there's more than one channel that leads to these explosions that we classify as 1As. We actually have some conflicting lines of evidence that say that maybe there's more than one channel. And so the cosmologist would need to know, right, so if I observe a 1A, am I putting it in the same box as all the other 1As I need for my analysis? Or am I putting in some uncertainty that I can't control for?
Right, and that was my next question. Is there any flavor, any different flavor of the 1As? Or are they all, they're used as a standard candle. Are they precisely the same?
So, no, they're not. We have the normal type 1A supernovae. These are the ones that we use for cosmology, the ones we can standardize. They're pretty much vanilla. They're not all exactly the same. Some of them are brighter, some of them are fainter, but we can standardize them. But then we have overluminous type 1A supernovae. We call them 91T-like, or for one that blew up in 1991. Then there are subluminous ones called 91BGs. And then there are There's a completely different subtype called 1AX, which may come from a different type of explosion. We never use those for cosmology. They're not on the standardization scale. And then there may be some type 1As that have interaction with their environment after they explode. Those are the ones that may tell us that there's more than one channel. But all of these are not used for cosmology. Only the ones I called normal 1As are used. But even then, I mean, we empirically standardize them. But they could still come from more than one channel physically.
What's left over? You know, when this thing goes off, what remains?
So again, it depends on your scenario. If what blew up was two white dwarfs that merged, nothing will remain. It'll just spew all of its innards all over space, and we'll have
awesome.
a very beautiful supernova remnant. If, on the other hand, the binary companion was a main sequence star or a red giant, then that should survive. It'll get a kick, it'll be flown out of its orbit, but it should be there. And so far, we haven't seen any such companions. People are looking for that.
And so let's talk a bit about another kind of event that seems to be caused by degenerate collisions or interactions. These are gamma ray bursts. So where is the sort of the separation between what seems to be causing a gamma ray burst and what seems to be causing these type 1A supernova?
That's a wonderful question, because we don't really know. So gamma ray bursts are a big mystery. We're not quite sure what is the engine that drives them. To complicate things, there are some gamma ray bursts, some GRBs, that seem to have supernovae associated with them. Those supernovae are not 1As. They're another type that we call broadline 1Cs. But to complicate things even further, not all broadline 1C supernovae have GRBs associated with them. So why? Are these different physical processes? Are these different stellar systems that are exploding? Or is it the same kind of stellar system, but there's some parameter you can tweak that in some cases will just give you the supernova, and in other cases will give you the supernova plus the gamma ray burst? We don't really know. There are lots of ideas for how you could get this, what your engine would be. It could be a magnetar, a rapidly spinning black hole that then spins down and spews out jets, or it could be something else. We're still in the phase where we're collecting observations and trying to constrain these different models. We don't have anything dramatic yet.
So, you know, I like to offer people unlimited budget to build any kind of observatory, space-based or ground-based they want. This is my gift to you, coming to the Weekly Space Hangout. So if you could have this magical large amounts of money to build some kind of specific instrument to really help you get at some questions, what would you like to get answered? What would you like to try and figure out?
So actually, this instrument is already on the books.
Then offer rescinded.
This is LSST.
Yes, of course.
So LSST will find tens of thousands of supernovae every night. We have no idea how we'll be able to follow up even a fraction of these.
Wow.
We'll have huge samples of supernovae. I love statistics. I love statistical samples. Give me, 1,000 supernovae and I can work with it. And this is what I want. I want these huge samples of lots of all these different types of supernovae, and then we can look at all the different correlations we can come up with. We can slice them every which way we want, and I think then we'll be able to solve quite a few questions and hopefully come up with completely new ones.
Well, yeah, I mean that's what's great. I mean, I think people are so excited about these planetary missions, some of these big telescopes, but really, the Large Synoptic Survey telescope, this thing is going to be generating so much data. It's going to be a revolution in astronomy all on its own. I mean, I think we wait until this thing gets running. And when is it going to go live?
Last I heard, I think it was 2021.
Yeah. So not too
2020.
long. Yeah, and I think it's going to generate. I mean, it's going to be the big sleeper, super science tool. So prepare yourselves. It's going to find asteroids and supernovae and all of that. So I got one last question. This is maybe a bit of a zinger. Do you think that there's enough uncertainty in the kinds of observations that you're making to cast doubt in dark energy at all, or do you think that you really can depend on these Type 1As as standard candles?
So we don't have to depend on Type 1As. If we had to, then I would be very worried. But we actually have other types of measurements, completely different experiments, using baryon acoustic oscillations, for example, using the CMB, and these constrain the parameter space of our cosmological models in different ways. So in most of the papers published these days, you see a combination of these probes. And so you don't have to depend on 1As exclusively. And all of these give you the same kind of picture, where you need this dark energy. I think the question really is different. I think the question is, can we come up with a completely different cosmological model which doesn't require dark energy, but still explains all the observations and gives us new predictions that we can test?
Right. I've got a couple of questions from the viewers. Elad Avron asks, I'm obsessed with the possibility of a naked eye supernova. Is there anything in our vicinity we expect to go boom in the observable future?
Well, we like to say that we hope that Betelgeuse has already exploded, and we're just waiting to hear about it. I think that's the closest one in the Milky Way that I know of.
Yeah, there's Eta Carinae as well.
Eta Carinae has already had a few eruptions, and yeah, hopefully that should also explode.
I mean,
That would be nice.
I feel a deep sense of loss for the people of Betelgeuse, but that's a sacrifice that I think will have to happen.
Well, they should see it coming.
Yeah, exactly. Thomas Stranaker says, can we detect the bridge between stars before the go nova, and can we see a change in the transfer material in that bridge before a nova? And I guess the question is, like, you haven't even really detected that transfer material yet, right? You need something super close.
So we can. So if you're accreting hydrogen from another star, that hydrogen should burn on the surface of the white dwarf and will be visible in the X-rays. And then we call these super soft X-ray sources, and we do detect those. So I don't know off the top of my head if we've seen super soft X-ray sources that then go nova.
Right. Right. And then one last one from Ben Kalo. Will all the detected supernova, I guess from LSST, be in the Milky Way or outside as well?
No, they will all be outside. They'll be in faraway galaxies. Anything that blows up in the Milky Way, you won't need LSST for that.
Well, how often are things blowing up in the Milky Way? I mean,
could be
even the ones that we can't see, right?
Could be some type of supernova every 50 years.
Wow. And then it's just a matter of whether it's on our side of the disk or on the other side, obscured by the dust, right? Yeah.
Yeah.
Amazing.
And whether the rates I just quoted are correct or not.
Yeah. Well, we'll wait for the LSST to tell us, and then we can really know. Well, Dr. Graur, thank you so much for joining us for the Space Hangout.
Thank you
You're
for
going to stick
inviting me.
around and talk with us about all the space news. So, and then we can. But if people have to go, where can they find out more about what you're working on? I know you're not on Twitter. I respect that.
I'm not on Twitter, but I do have a homepage. They can just search for my name, and one of the first links that come up will be my homepage, including a PhD comics video about my work.
Okay, great. Okay, great. So let's get on with the stories this week. Oh, what am I most interested in? You know what? This is great. So Morgan, let's talk about Saturn's rings, because I recall a podcast a couple of months back where I asked you definitively, are Saturn's rings old or new? And you told me that you guys were pretty sure now you knew how it was. How sure are you now?
So it's still an open question, and hopefully in this podcast of the past, I also insinuated that this is a problem that we don't yet have a complete answer to. There's one school of thought that suggests that the rings are as old as the solar system. That would make them 4.5 billion years old, the same age as the moon, the same age as all the planets, etc. The other school of thought suggests that the rings must be much, much younger than that, hundreds of millions of years old. And the typical argument for why that must be is that the rings appear to be extremely, extremely clean. There's spaces just full of dust, micrometeorites, that sort of thing floating around, and if you're exposed to that over billions of years, you ought to get pretty dirty. But the rings are nearly 100% pure ice, clean ice. And that's long led some people to argue that the rings must be relatively young. This week we found out about a study that offered some support for that. Because in order for the rings to be old and yet be so clean, they must be extremely massive. There must be a lot of material they're able to absorb all of that dust and kind of mix it up and still have a relatively clean percentage of ice. And we measure the mass of the rings by measuring its density and then multiplying that density basically by the volume to get the mass. And the way we measure the density is by studying waves that travel through the rings. So if you've ever seen a picture of the rings of Saturn, you kind of see all those striations on it that make it look sort of like a record. Each one of those striations is a density wave that's been launched by gravitational interactions with a moon. And by measuring those, we can estimate the density of the material that wave must be traveling through. And the problem that we have is that one of Saturn's two big rings, the B ring, this is the closer one of the two that you could see if you looked out with a home telescope, appears to be extremely dense. It's very difficult to see light shining through it in order to measure these waves. And for a long time, we've assumed that it's because it's difficult to see through, that must mean it's very heavy. There must be a lot of material in there in order to block that light and make it appear dense. But what this work did was take basically all the observations of this B ring that we had and rotate them all so they lined up and they stacked them up. And when they stacked this up, what they were able to do was reveal some structure, some of these waves within the B ring that weren't visible in any single observation, but were visible over the course of time by adding up lots of observations together, kind of like taking a longer picture of the rings. And then they used those waves to measure the density of the material through which it was moving, just like we've always done. And what they found was that the density was far, far lower than what we expected for this area of the B ring. And if the density in the B ring, the most massive part of the rings, is low, that suggests the density or the mass of the whole ring system must be relatively low, and thus the rings must be relatively young. And go ahead.
I was going to say, so we always say that the rings are gossamer thin, no thicker, or they can be as thin as 10 meters thick at some of the thinnest. Does this mean that maybe they're even thinner?
It could. It's what's happening here is a question that's still very contentious. And so one possibility is that what we're seeing are the material that makes up the rings. The ice particles are extremely puffy. They're kind of like cotton balls. And so they take up a lot of space and block a lot of light without weighing a lot. And that's one possible explanation for how you could get this. Another possible explanation is that for some reason the material within the rings is arranged in some sort of structure that tends to very efficiently block light. Because you can imagine you could very easily make a perfectly opaque system if you packed one by one by one ice atoms next to each other with no space between them. And
I mean, you look at fog as compared to a pool of water, right? There's way less mass in fog, and yet it blocks the light very well.
Right, and so it could be that some structure in the B ring blocks a lot of light, again, without using a lot of mass. And so this calls into the question some of our fundamental guesses about the way in which the main rings of Saturn work. And hopefully we're going to have another independent way of measuring this right at the end of the Cassini mission. Because over the course of the next year and a half, as the Cassini mission ends, it's going to begin to become more daring. And we've stayed a long way away from the rings for the last 12 years because striking even one ring particle could cause irreparable damage to the spacecraft. But what we're going to do is we're actually going to fly between the rings and the planet.
That's going to be so awesome.
Outside of the rings. And when we're in between the rings, we'll have Saturn's gravity tugging on the spacecraft in one direction, and the gravity of the rings tugging on the spacecraft in the other direction. And this should, we hope, allow the Cassini spacecraft to make a direct measurement of the mass of the rings, instead of the indirect measurement that we've made by trying to infer these densities, then multiplying by the volume and getting the mass. And
what about going through the rings?
So we couldn't go. I mean, we could fly the spacecraft through the rings, but that would almost certainly destroy the spacecraft, because Cassini's traveling at several times faster than the speed of a bullet, and so you can imagine at that speed, even a grain of sand would rip right through the basically tinfoil skin of the spacecraft and wreak havoc on the instruments inside. And so we're going to fly basically as close as people are comfortable to going, but no closer than that. And the hope is that'll allow us to make this measurement, nail down once and for all what the mass is, and that mass will tell us, are the rings young or are the rings old?
That's awesome.
I have a question.
Go ahead, Jolene.
Just because the piece of sand comment, so does that therefore mean that the spacecraft is not encountering, I mean, because we know space is comparatively pretty empty, but so it's not encountering any sand at all, not even little tiny dust particles whipping about the cosmos. Like, that's how empty it really is out there. So
we do hit dust particles, and so we're worried about things just a little bit bigger than that. But it does encounter dust very infrequently. I think if I remember, it was about a 4-year journey. No, it's a 7-year journey between the launch on Earth and arriving at Saturn, and over that 7 years, Cassini encountered something like 100 dust particles over the course of 7 years. And one of those was traveling fast enough to hit the dust detector and do some damage to it. And so every spacecraft is basically playing roulette with the fact that a penny-sized piece of dirt would just annihilate an instrument on one of these spacecraft at the speeds
as are any future astronauts.
Absolutely. The astronauts that traveled from the Earth to the Moon outside the protection of the Earth's atmosphere and the magnetic field were constantly at risk of being struck by a micrometeorite that would have punctured their spacecraft irreparably. But the odds are very low, and space is fortunately quite empty.
Okay, so Sondi, let's move on to your story this week, and I know you've got to head out pretty quick. So why don't you tell us about 67P? Oh, you're muted, Sondi.
Our friend Morgan has been talking about the rings of Saturn, which are mostly ice and not necessarily made of dust. Thank you, Morgan. I also want to point out that Morgan is saying, well, getting hit by a particle of dust that's moving really fast would cause irreversible damage to the spacecraft. But the other thing that causes irreversible damage to your spacecraft is flying Cassini into Saturn next year. So spacecraft is doomed anyway. All right, so we're talking about 67P, and they recently released information that 67P is not primarily ice, like something like Saturn's rings. It's actually primarily dust, and that it's really fluffy. It's kind of more like styrofoam than a bunch of densely packed pieces of sand, which is sort of interesting. That it's really kind of an icy mud ball rather than a dirty snowball, that it's mostly kind of dirt rather than mostly ice.
Whoop.
Are you there? Okay.
Yeah. We're here. We hear you.
Okay. So yeah, the term for this is called porosity, which has to do with how densely packed all the particles are. So these things are it's pretty much not porous, but the other thing that's interesting about this new result sort of came out yesterday was that there's not sort of large voids in the comet. There aren't gigantic caverns. So while this comet is very fluffy and not particularly dense, it doesn't have giant holes in it. So the particles aren't packed very tightly, but they aren't packed very tightly on a micro scale. On a macro scale, they're pretty evenly distributed. We're not seeing huge empty caves.
So you can't
go anything on Comet 67P. Sorry?
What's the thing on Earth that we are familiar with that would
Styrofoam.
be styrofoam?
Styrofoam is what sort of, it's sort of very light, it's very fluffy,
Mhm.
and when you take apart the piece of styrofoam that your computer comes packed in when it's shipped to you, you don't find, there are, sort of, if you were to slice open that styrofoam, you wouldn't find large caves. But the material itself is sort of packed in a way that it's very light and fluffy without giant holes in it.
I'm kind of imagining, anyone who's a skier, there's a kind of snow called corn snow you get in the spring, and it's like just like little pebbles, but they're snow. I'm kind of imagining that, and they would not make any caverns, but are but it's definitely not like fluffy snow, and it's definitely not a big ball of rock. And
yeah, it would be more like the crud that's on the side of the road after the snowplow has gone by too many times, and it's got lots of road grime mixed in. It's really dark, and if you actually went up to Comet Churyumov-Gerasimenko in a spacecraft and looked at it with your eyes, you would see it's a really dark object. All these comets are really dark. We just overexpose them so they look really light. But the thing is that the fact that Comet Churyumov-Gerasimenko is sort of fluffy makes it really similar to a lot of the asteroids that we look at as well, which are these rubble piles or fairy castles, or in polite company we call them gravitational aggregates.
So is that sort of the way this is heading now? The structure of these objects is less and less like, when you think about everything that Star Wars has taught us. We're imagining sort of potato shape.
Everything Star Wars has taught you about asteroids is wrong.
Okay, fine. But
that's a story for another time. But you want to think of this comet as less like a Katamari ball of like a bunch of random stuff stuck together with like big voids and caverns, and more sort of like a pile of kind of frosty dirt that's very uniformly distributed.
Right. Well, the asteroids are more like Katamari balls.
The asteroids are very similar to Comet Churyumov-Gerasimenko. We think that they've got small things evenly distributed, and they don't have giant void spaces on them.
Right.
Cool. Yeah, I don't know. I think it's cool that these comets are more dirty than icy.
Yeah. So I would like to see a sample brought back from
We're working on that.
Asteroid.
We're working on that. Well,
That's
sample
great.
brought back from an asteroid, 2023, mark your calendar, and sample returned from a comet, get excited, it might happen in the next round of New Frontiers, so.
Yeah, you're on the job, Sonny. You're our representative.
I actually am.
Bring back. I know, that's why I brought it up. Okay, let's move on. Let's see, so Carolyn, let's talk about where the moon might have come from.
Okay, well, so in browsing through all the stories I get this week, I had one catch my eye that a group of geochemists from the University of California at Los Angeles decided to take a look at some moon rocks and also some rocks from Earth. So they had 7 rocks from the Apollo missions 12, 15, and 17. And then they compared those. They did a big chemical analysis on these, and they also analyzed 6 volcanic rocks from Earth's mantle that were collected in Hawaii and Arizona. So the idea was to basically look at all the chemical elements in these rocks and find out if they could make a case for better zeroing in on the formation of the moon from a chemical analysis standpoint. So they did this complex chemical analysis using a new mass spectrometer. And without getting into all the gory details, what they really found was that when you compare the elements between the two sets of rocks, and in particular you look at specific isotopes of oxygen, the two rocks turn out to be very, very, very similar, in fact, almost identical. So this is a little bit in contrast to studies that were published a couple of years ago, several years ago, saying, well, those isotopes are slightly different. So the astronomers, the scientists were basically looking at trying to find a scenario for what would cause the rocks to be similar instead of being slightly different. And as it turned out, they found that in 2012, another scientist suggested that a head-on collision between Earth, the baby Earth, so 4.5 billion years ago, and a sort of a Mars-sized object called Theia, we've all heard about this, basically they smacked into each other head-on. Previously, people thought it would have been sort of a glancing blow, that maybe they just sort of sideswiped each other. And in that case, the rocks that were shaved off from each of the worlds or blown apart would not have mixed very well. As it turned out, if you do a head-on collision, then you get more mixing of the rocks. So Theia didn't really survive this whole head-on collision. During the collision, the rocks from both worlds mixed really well. They combined to form the moon, and there's still pieces of Theia on baby Earth, well, on Earth today. So it basically polluted the baby Earth. We still find those rocks. So essentially, Theia was mixed into both worlds, and we find much of it on both places. So you would only get that kind of mixing if you had a head-on collision instead of this sort of side-swiping collision. And I think the takeaway from here is that we now really can say the devil is in the details in terms of how the moon is formed, and there are really some very minute chemical changes, chemical differences, or no differences that can tell us one scenario over another.
So really, the Earth and Theia turned into the Earth and the Moon, and we really, we always say that something crashed into the Earth, but Theia was a pretty big planet when it happened.
Yeah, and so what you have left is Earth with some of Theia and Moon with lots of Theia. Theia, I guess is how it's pronounced. And so the way that you tell now as you look at the rocks from both, and they're getting better and better and better at looking at the chemical makeup of these rocks and comparing them, you're getting down to the isotope level and being able to say, okay, if these isotopes are essentially similar, what scenario could we have? And instead of just having it smashing in and maybe a lot of it running off to space, we have all of it falling back together to form the moon and essentially scattering stuff all over the Earth.
Well, we thank Theia for its sacrifice.
Yes, we do.
All right, let's move on. We are running a little out of time, so and Jolene has had a chance to tell us about those cunning Earth-hiding stars.
Yeah, so this actually deals with Espresso, which is supposed to come out next year. It's a new way of hunting for planets. And just sort of like a little preamble, we found a lot of planets so far. The thing is that most of these planets are enormous, which is fantastic because gas giants and planets that are 10 times larger than Jupiter are super, super interesting, but they aren't exactly the best things for Earth 2.0 or life as we know it. So one of the things that we want to try and get better at, and indeed that Espresso is looking towards, is finding Earth-like planets that aren't just about the same size as Earth, but they are also orbiting sun-like stars, because again, life as we know it probably most likely to be found on stars that have a similar brightness and energy output to our own. So to that extent, the problem that we run into with this technology is that essentially what it does is it measures how much stars move as a result of these really small Earth-sized planets. So with the current technology that we have, which is HARPS, it is able to measure movement caused by planets that orbit stars similar to our own that are about 10 times the size of Earth, which is relatively speaking not a significant difference, but it's significant enough that we really probably couldn't live on those worlds or have life as we know it. And so what we need to be able to do is measure movement that is equal to 0.3 kilometers an hour. And we have to be able to measure that movement on stars that are like billions of kilometers away. So it's exceedingly, exceedingly difficult. Espresso is able to measure movement that is 0.35 kilometers an hour. So it's super, super close. And so this week, one of the scientists working on a team did an article in which he was talking about some of the pitfalls and perils that we're going to encounter with this new tech. And one of those is something as silly as sunspots. What happens with sunspots is they're dark areas on the surfaces of stars, and they change the radial velocity, of the stars. So when we're looking at these, they can cause a difference that's equal to, I think it's like 7.3. So if we're looking for that's how much, like, kilometers an hour. They can make it look like the star is moving that much differently than what it actually is. So we're trying to measure 0.3 kilometers an hour. These sunspots are causing 7.3 kilometer an hour difference. So it's just going to be extremely, extremely difficult with verifying whether or not various stars actually do have Earth-sized planets around it because of these sunspots. So hopefully, though, within the next couple of decades, we'll refine those techniques and be able to use Espresso and stuff to have a host of potentially Earth-like worlds that we still couldn't actually reach. But at least we know we're out there, so that's pretty cool.
Yeah, I'm still waiting for that. Oh, I'm getting an echo from you. You need headphones. Oh, I have no follow-up question then, and we should probably move on anyway. So let's go back around. Morgan, let's talk about NASA's shaky plans for Mars.
Yeah, so NASA was kind of in the hot seat this week in front of the House of Representatives committee that governs space, and they were looking into NASA's stated plans to go and send humans to Mars. And this has been NASA's plan now for the majority of the Obama administration. And the panel that was being interviewed, as well as many of the representatives doing the questioning, seemed quite sour on NASA's plan. Specifically the plan to build the Space Launch System and the Orion capsule, to send astronauts in orbit about the moon, to send astronauts then onto an asteroid and ultimately onto Mars. And this was characterized by some as basically being unfocused. And one expert from the National Research Council, which is the investigative arm of the American Academies of Science, who completed a report a couple of years ago about this program, said that NASA needs two things in order to get to Mars. They need laser-sharp focus, and they need an increase in their budget, and that thus far they're not getting either of those. And even if we canceled the International Space Station tomorrow, over the next 20 years, NASA would have about $180 billion to spend on human spaceflight. When this panel estimates to get to Mars, you would need about $500 billion. And so they're not nearly there. Also, their mission keeps changing too frequently, from going back to the moon, to going in orbit about the moon, to going to an asteroid, to going to Mars, and that the 20 to 40 year commitment necessary to get people into orbit and ultimately onto the surface of Mars is something that NASA isn't capable of today. And the questioning got so harsh, in fact, that at least one representative suggested something that many scientists are in favor of, which is abandoning the human spaceflight program entirely in favor of increased robotic exploration. And they saw this as a much more cost-effective way to explore the solar system at a time in which the federal government is looking to reduce the amount of money it's spending, not increase it by $500 billion.
And, you know, if you're not going to come up with a really firm, committed, long-term strategy, that makes a ton of sense.
It absolutely does, and I've said now for years that I'm fully in support of putting humans on Mars if we commit to doing it. But a halfway commitment just burns hundreds of billions of dollars with no ultimate end, and that's money we could save. That's money we could put to putting New Horizons-style flybys of every object that we wanted to visit in the solar system, putting a Mars rover on every solid planet in the solar system, and we'd still have the majority of that money left over to spend or to save.
Yeah, or even a milestones-based just capabilities improvement on the ability to do human spaceflight. So just as long as each step is a push forward into new places, now we're docking with an asteroid. Now we're sending a bigger spacecraft. Now we're building things in space. Now we're, I always look at the Gemini program as sort of what I felt was like the greatest way that worked, because every mission they weren't trying to go to the moon, although that was still in building up to it, but they were just enhancing the capabilities. How long can two people stay in space? How long, can we dock in space? Can we, and so on and so forth. And they just kept pushing the capabilities, mission after mission after mission. And that feels like that's the equivalent of what's going on with the robotic program now, right? Like, let's put a rover on Mars. Now let's put a rover that can find, that's bigger, and now let's put one that's nuclear powered, and now let's put one that will send a sample back, etc. Right?
Right, and unfortunately, coming next year, we'll have a change of presidential administration, and that's likely to trigger a reevaluation and perhaps a complete redesign of NASA's priorities, and that's likely just to set them back at square one once more.
Yeah.
And that's exactly what this panel was complaining about, is that in the current political and fiscal environment, getting 20 to 40 years of stability is just, we're lucky to get 4 years of stability these days.
But if you did the capability side, then you could, with maybe a 5-year commitment, make it be a Mars mission. You've already built up the launch systems, you've understood how to keep people alive in space for long periods of time. We've got spacecraft going to and from Mars on a regular basis, like in The Martian. Then you can extend out these smaller goals that could fit within an administration. So
one of the things that a lot of people were talking about is focusing more on the moon. That's not to say that we just go back to the moon and be happy and content with that, but realistically, getting people to go to the moon, having them be on the moon in sort of the incremental way that you're talking about, is a much more viable plan to help us develop those technologies, so that then we can sort of refocus. Big jump, I suppose.
Yeah. Oh well, Elon Musk will do it anyway. So, Carolyn, let's talk about chimps in space.
Okay, let me just the last thing that Jolene said. We actually did do, when I was working with the case for Mars a long time ago, we did have this incremental set of places we would go to, to basically orbit the Earth, build things to get to the moon, learn how to live on the moon so we could learn how to live on Mars, and then eventually get out to Mars. So that infrastructure, that discussion infrastructure is there, and we do see that in some of the missions that have gone to Mars, but of course not all of them. So going back even earlier, I'm working with an online company called About.com, and I'm revising a lot of the really older images on the spaceabout.com site. And I ran across this fascinating article about chimps in space, primates in space, essentially. And the gist of the story was that for NASA, back in the early days, and in fact back as early as in the late 1940s, chimps and other primates basically were the way that we tested our life support systems and ways to get to space. And later on, after watching NASA do this, sending up these monkeys and all kinds of other animals, then the Soviet Space Agency started to get involved in it as well, and they sent up the dog. We all know about Laika the dog, and we had mice going up and insects. Essentially, these were used to test these launch systems, life support systems, that sort of, see if we can actually get something up to space, make it survive, and then come back. So I was kind of surprised to see that the NASA Primates to Space program actually began in 1948. The very first monkey was called Albert, and he went up to space aboard a V2. Unfortunately, he didn't make it back alive, but the next one after him did. He was Albert 2. And he went up and made it, basically was the first monkey in space, the first primate to go to space. The ones that I remember specifically as a kid were Ham and Sam, and they were launched to space. And what's left of Ham is actually buried in New Mexico, a few hundred miles south of me, at the International Space Hall of Fame in Alamogordo. He was the last monkey to be launched before Alan Shepard made his maiden flight in 1961. He wasn't the last. There were many more to go up. But by the end of the 1990s, the sort of primates to space stopped because people were getting very worried about the, sort of the ethical implications of sending these primates to space. We still send up mice and bees and all these kinds of other things. But anyway, I just sort of tossed the story in because I found it a very interesting piece of space history, and I thought maybe the listeners would like to hear about it.
So if they go to about.com/space.
That's space.about.com.
Right, and it's hopefully fairly
Yeah, I think
prominent
it's
there.
story in the
Sounds
comic.
great. All right, Jolene, I'm going to give you the last word. Talk about a black hole in a superjet.
Conveniently, this is super simple and straightforward, so I can do it in just a second. Chandra was looking at Picture A galaxy that's 500 million light years away, and they observed some X-ray emissions. This big, huge line of like a huge jet that's shooting out of the black hole that's at the center of this galaxy, and they found that this jet is 300,000 light years long, which of course is enormous. And for some perspective, the Milky Way galaxy is about 100,000 light years in diameter. So this jet is literally 3 times longer than our entire galaxy.
Awesome.
Yeah.
And I'm not getting an echo, so is this a fairly common thing out there, jets like this?
Black holes do have jets. I actually don't know off the top of my head how common it is to see ones that are this size, but I do know that one of the things that scientists are trying to figure out is that with this particular one, because it seems to be so long, the X-ray emissions, the electrons that are swirling around the magnetic field and getting shot out, they think that they must be getting reaccelerated as they go along in order for the jet to be so long, and they don't know exactly what's causing that. There were some ideas that perhaps the electrons are interacting with photons from the cosmic microwave background radiation, but they ruled that out. So the search is on to essentially find what's causing this phenomenon.
Dr. Graur, I know you've been sticking around and listening intently. This feels a little in your wheelhouse. Have you done any observations on quasars, on jets like this, supermassive black holes?
I have not. Actually, active galactic nuclei like these ones are one of my contaminants, or the kind of thing I need to throw out of my sample.
So you'd wish they'd all go away.
Oh yeah.
Yeah, that's funny. When you say it's a contaminant, is that because it looks enough like a supernova explosion that it's actually, can kind of fool your observations?
So when we discover supernovae, we usually do this by subtracting one image of the sky from another taken at a different time. And then we just look for little points of light. Now, you find a point of light that is at the center of its galaxy. Is it a supernova, or is it a black hole that which flux is changing over time? I really don't like it when it's
that's okay. Well, we'll see what we can do to get rid of them then, because it's not good for the galaxy that they're in. Although there's one theory that in fact these jets might help promote star formation in other galaxies. That, as you said, Jolene, they go so far out and they actually rain down material. It's possible they rain material back down into the galaxy and actually trigger star formation. So maybe we need them. Anyway, all right. Well, I think we can get to wrapping up this week's episode of the Weekly Space Hangout. So I want to give everyone a chance to let people know where they can find out more. I want to thank of course, the wonderful WSH crew, especially this week as we went through all of the technical issues to try and make this show actually happen. So thanks everybody's patience. But if you haven't already checked them out, search for the WSH crew. You should find the Google Plus community and their website and their Twitter handle, and you can join in. And they really are the producers of the show. They organize the guests. They tell us what to say. They tell us what stories they want to hear. And I couldn't be more happy to work with such a great group of people. All right, so Carolyn, where can people find out more about you? Oh, you're so muted.
Yeah, I am. Here I am. You can find me at thespacewriter.com or on Twitter at @spacewriter.
And of course, the work you're doing at space.about.com.
Yes, thank you.
Yay. Jolene, where do people find out more?
There is Futurism, the Twitter account, also Futurism on Facebook, futurism.com, the website, and pretty much all other forms of social media. Hooray!
Morgan.
I'm amazed that you're able to get that Twitter handle this many years into Twitter. But you can find me on Twitter at Morgan Rehnberg, and check out my website, morganrehnberg.com.
All right, and Sondi had to go, but she's of course at Sondi everywhere. Website, Twitter, etc. So of course I'm F. Cain on Twitter. You can subscribe to this YouTube channel wherever you're watching it. Dr. Graur will give you the last word. Once again, where do people find out more about your work?
So I'm a little old-fashioned. You can find me on the internet.
Just do a search. Your name is very searchable, I think.
You won't find that many other hits, no.
Great. All right. Well, thanks everyone for joining us. Thanks to the panelists, and thanks for everyone putting up with the technical difficulties that we had. And we'll see you all next week.